And this is T of AE1 plus BE2. Because that thing's E1 and that thing's E2. Now, what do I know about linear transformations? Linear transformations break up. This is A TE1 plus B TE2. And what do you mean? I know exactly what TE1 and TE2 are, correct? So now I've got to do is just plug it in the computer, right? This is A times the vector, whatever it was, minus 1, 0, 1, and 1. And this is B times 2, 1, 1, 2. And so I can put this together into some single vector more fancily, if I so desire. This is negative A plus 2B. This is 0 plus B. This is A plus B. And this is A plus 2B. But here's kind of a rub. This is actually equal to everybody agree with that? I mean, you can check it, right? It's this row times this column should be the first entry, which is negative A plus 2B. The second entry, it should be this row times this column, which is 0, which is B, and then A plus B and A plus 2B. How about that? So just from that, first of all, there's a couple of really cool things going on here. The first thing is to determine this entire function. I mean, there's infinitely many things in the domain. There's infinitely many vectors in R2 that I can put in there. All I needed was 2 pieces of data, and that told me everything, what it does. And number 2, there's my matrix, right? This matrix completely governs what this linear transformation does. Everybody? Okay, any questions? Yes, sir.
Well, we're going to find out what APR.
Well, see, that's the beauty. A and B can be any freaking thing you want. Pick your favorite A and B, 3 and 2, whatever. And you are, of course, referring to this A and B, correct? Yeah, because any vector in R2 is this. It's something A, something B. You've got complete freedom on your choices of A and B. And this gives you a complete formula of where that vector will go. Right? So, for example, the vector 1, negative 1 will go to negative 3, negative 1, 0, minus 1. Okay. Let me give you kind of a theorem that sort of encapsulates this example in a more general sense and gives you a nice formula. By the way, look at the matrix that we made. It should play familiar. Because at the beginning of the problem, this was TE1 and this was TE2, right? These were the 2 items of data that I started with, right? So let me kind of wrap that up into a theorem for you. Let's let T go from Rn into Rm. Be a linear transformation. Then there exists unique matrix. A such that T of X is AX for every vectors X that live in Rn. Okay. And let me tell you what matrix is. Let me tell you exactly how to make this matrix. This is PE1, PE2, PE. So you make the matrix out of column vectors, and the column vectors are where respectively E1, E2. So they'll be starting in Rn, they'll be TEN, where all those go. So in particular, to determine the linear transformation from Rn to Rm, you only need n pieces of data. You need to know where these EIs go, and you're good to go. And actually, because I think it will sort of familiarize us a little bit with notation, let me do a computation to verify this. Let me make an observation. Let's start with X, any vector you want in Rn, any vector. Like in the previous example, my vector AB in R2. Take this vector. Okay, that's a silly observation. All it says is, remember, this right here is a vector in Rn. So this is an n by 1 vector. This is the n by n identity matrix. And this is an n by 1 vector. And really all it says is X is the same thing as the identity matrix times X. And I just verify here that the size is right for multiplication. And the identity matrix is, of course, E1, E2, En. So this is just the identity matrix times X, same thing you've got there. And of course, this is so if vector X to be written in this form here, because it's got n rows, it has these n entries, then remember this thing is the same as this. So now I am prepared to verify that my matrix here works. So let's look at T of X. Well, now I know what X is. This is T of X1, E1, X2, E2. Because this X vector is just this. So I just replace X vector by what it is. Now, this is a linear transformation. So can anybody guess what my next move might be? T of the sum of this big collection of things. What can I do? Okay, good. I can break this up. So this is, and in fact, I can also pull out constants. Yes,
So you could pull out constants from transforms, but not sectors or.
that's right. You can't pull vectors out, but you can pull any constant out. And using the same notation, this is the same thing as T design in times vector x. Which is, if I call this matrix A, is it over here? In the theorem, A is this. This is A. So this little procedure always works. So if I walk up to you on the street and I give you the data for this linear transformation, so I'll tell you where E1 goes, E2 goes, En goes. All you have to do is take what I tell you, take those column vectors and make a matrix, and that matrix will work for every vector. So that'll determine your transformation for every vector. Okay. Any questions? So let's do a couple of examples. Let's see this in action. So here's one example. Give me a number. 9. Okay. So let's do this. I'm going to have T of X equals 3X. No, I'm not. I'm going to do 9. But actually, there, I'll do the number. Okay, here's my linear transformation. I want to take any vector in three-dimensional space, wherever it may be, and I'm going to basically triple its length. That's what, no, not triple, like 9 times its length, right? I'm going to make that sucker grow, right? This is a linear transformation. In fact, we verified this multiplication by scalar. So here's a linear transformation. So I want to know what my matrix is. Well, let's just kind of build it from first principles. Now, what does this linear transformation do to E1? Yeah,
A 1.
that's right. Basically, all it does to E1 is multiply it by 9, right? So there you go. You got 9, 0, 0. And the same with these other linear transformation that we have here. Basically just grows those 3 vectors by factor of 9, right? So my matrix, if I wanted to write this matrix form, is this. A is equal to 9, 0, 0, 0, 9, 0, 0, 0, 9. Notice that this is 9 times the identity matrix, and this is not a coincidence. And let me just kind of hardcore write this out so that we can actually see what happens. So let's just explicitly see what happens here. This row, this column, that's going to be 9x1 and a bunch of zeros. This row, this column, 0, 9x2, 0. Last row, this column, 0, 0, 9. And what is our linear transformation done? It's neatly multiplied that thing by 9. Here's a fun one. I kind of hinted at this last time. How about this? I want to do something similar to what I did last time. I'll do a little twist on this. Let's I'm going to describe this. Okay. X 60 degrees. Yes.
I just have a question. Would it always go from like R2 to R2, or could it go from like R2 to R4 or something?
Oh, sure. You can do anything. Right. In fact, our first example went, I think, from R2 to R4. But yeah, and this theorem always works, right? All you need is all the EIs from the domain, and that'll determine the matrix. Okay, so basically what happens? Just like before, what this does is this takes every vector and it rotates it by 60 degrees, right? Same length, that's supposed to be the same length. They didn't do it very well, but it rotates everything. Basically, it's like you screw the entire plane 60 degrees counterclockwise. This is a linear transformation. We kind of described that last time. It's the matrix. Well, I mean, this sounds very confusing, right? Because there's a lot of stuff kind of getting turned here, right? Goodness. But the really groovy thing is we only need two pieces of paper. So let's find where E1 and E2 and you know what, I think even I can handle that. And this is actually like a retro Friday here, baby, because what we're doing is we are basically doing some trig, right? Because how long is the vector E1 and E2? How long does it look like they are? They're of length 1, so when you rotate them, they're all going to sit on a unit circle, right? So let's see what happens. E1 starts here. And this is on the unit circle x squared plus y squared equals 1. And it rotates 60 degrees for power 3 radians. So it ends up here. So T of E1 ends up here. How can I figure out what the coordinates are? This power 3 radians. Yes.
The next coordinate is more cosine theta. The x coordinate is more cosine theta, and the y coordinate is more sine theta.
Oh, you sound like a physicist. That's exactly right, right? The x coordinate is r cosine theta, and the y coordinate is r sine theta. And what makes it easier for us, what's r in our case? 1, because we're on the unit circle, right? So basically, the x coordinate should be cosine of power 3. And the y coordinate should be sine. Everybody agree with that? And the cosine, if I remember right, should be that. So what happens to T of E1? It ends up at 1/2 in radical 3/2. Now, what we got to do is figure out where T of E2 goes. This one rotates power of 3 as well, right? So actually, I guess I need to figure out the total angle here, right? What is the total angle here? So this should be, it should be the same thing, cosine of something and sine of something.
Cosine of 2/3 and sine of 2/3.
I know why you say that, but you're off a little bit. Right, because yes, this angle right here is power of 3, right? But where did you start? Started at power of 2,
Oh,
right? So this total angle here should be power of 2 and another power of 3, right? Everybody okay with that? So that's 3 power of 6 plus 2 power of 6. This should be 5 power of 6. Which in this case should be minus radical 3/2 and 1/2. Everybody understand? So this ends up at minus radical 3/2 and 1/2. So which is this mess. 1/2 radical 3/2 minus radical 3/2 1/2. And that'll work for any vector, not just that E1, E2. Take any vector here and put it in there, and that matrix will take that thing, it'll leave the length the same, and it'll rotate it 60 degrees counterclockwise. Let me give you a fact that you should try to verify here. So I'm gonna leave this kind of open ended. What does a matrix cosine theta sine theta minus sine theta cosine theta? That's my generalization of the previous example. See if you can verify that that actually takes any vector in R2 and rotates it counterclockwise by theta radians. Okay. Any questions? Yes.
so for like that problem, can you just assume that it started on like cosine 0, sine of 0, and then like move 60? Like what if it started at like 20 degrees and then after?
Well, see, that's the magic of it. Even if your vector start, once you've got this matrix worked out, whatever we got over there, the 1/2 minus 3 has 1/2. It doesn't matter if your angle starts at 20 degrees, it'll still rotate to 80, right? It always works, right? All you need to determine the matrix that works for everything is just what happens to those first two vectors. And in fact, we'll see it doesn't even have to be these two particular vectors later. Okay. I would also, in playing around with this, let me reference you to. There's a couple of pages in your text where they have pictures of fishes and they reflect about various axes. All of these examples they have in here are variants kind of this or similar ilk. You might look at those and see and kind of practice what these matrices do. Let me give you a couple of definitions here, kind of the end game, and then maybe we'll come back to another example at a time. Let T from Rn be a linear transformation. Someone had kind of two definitions here in parallel. And by the way, this doesn't have to be a linear transformation. This definition holds for any function. We say T is onto. How many of you have ever heard a function being onto? You might have heard this in calculus or pre-calculus, especially when you talked about invertible functions like this. So what this means is if each P is Rm is the image of at least one B in Rm. That is to say, T of B. So that's kind of part A of the definition, if you will. This is what it means to be onto. It basically means everything in Rn is covered. I'll try to clarify that in a moment. Number two, or the second part of the definition, is T from Rn and Rm is 1-to-1 if T of X, if each B in Rm is the image of at most one vector in Rm. And let me also state it this way. Equivalently, T of X equals T of Y implies X and Y have to be the same. So actually, let me kind of draw you a picture of this. Sort of illustrates this concept of this. And this is a very important concept, not just linear transformation functions. How many of you have ever heard 1-to-1? Right, you might have heard that. In the context you might have heard it, it's usually when you were talking about inverse trig functions. That might have been the first place where you encountered it, either in pre-calculus or calc. How many of you have ever heard of, does anybody know what the test for function is? How many of you have heard of the vertical line test? Right? If you can draw a vertical line and it hits the graph in more than one point, it's not a function, right? How many of you have heard of the horizontal line test? If you can hit the graph in more than one point with a horizontal line, it's not 1-to-1. So Here's kind of a diagram of one-to-one on. So here you have Rn, and your linear transformation goes to Rn. What it means to be onto is it means everything in the target, everything in the codomain is covered. So if you have some B over here, then there's some B that goes to B. Right? Any B you want is covered by something. So what it means to be onto is over here, no one is lonely. Everybody has somebody going to it, right? Nobody's lonely. Everybody has, right? Because with some functions, you might have a B over here with big tiers that nobody goes to that, right? For example, if you have the function y equals x squared, no negative number gets mapped to by that, right? There's no negative number that's a square, right? So they're all lonely. Nobody's lonely for an onto function. One-to-one. What one-to-one means is everything is the image of at most one. Right? So that means, so I like to write it this way, T of x equals T of y means x equals y. It means no two vectors in domain and go to the same vector in target. So basically, I'll illustrate this by what it's not. This cannot happen. You can't have two different vectors going to the same one here. So one-to-one means no one is jealous. You can't have two vectors wanting to date the same vector over in the target. Okay. Here is, any questions? Yes.
So we're on to go to the vectors in the domain, go to the same.
Great question. Absolutely they can, right? You can have jealousy for onto, and you can have loneliness for one-to-one. Yes. So here is a theorem. 3 more theorems per day. Let T go from Rn to Rn. This is actually a super useful theorem because this actually gives you a computational way to determine whether a linear transformation is one-to-one or not. T is one-to-one if and only if Tx equals 0 has only the trivial solution. So if you take Tx equals 0, remember we now know I can write that as a matrix, right? So take the matrix for T and set up that system of homogeneous equations. It will have 0 as a solution. If that is the only solution, then it's one-to-one. And if it's one-to-one, that'll be the only solution. And let me give you one last theorem here. And then maybe I'll demonstrate that previous one. Theorem. Let T be a linear transformation from Rn or M with matrix A. Okay, so suppose you go through the trouble we went through in class today, you've got a linear transformation, you figure out what the matrix is. We'll call it A. Then A, T is onto if and only if the columns of A span R. And this is something familiar that we've had before, right? We know we've got a protocol for looking at a matrix and seeing if its columns span Rn. So, okay, that's how you determine that. And T is 1 to 1 if and only if the columns of A are linearly independent. And this uses this previous thing about the trivial solution. So if the columns are linearly independent, then it's 1 to 1 and conversely. Okay, any questions on that? Think about the connections in these theorems. Don't forget you got a quiz due at 5 o'clock today, and the connection will be due Tuesday. Questions? Okay, y'all enjoy first Friday and have a good weekend.